All right, welcome everyone. My name is Balázs. I'm here to talk about OpenMRN and specifically OpenMRNLite, which is an Arduino library for building devices based on the NMRA LCC and the OpenLCP bus. So let me talk a little bit about background, what is OpenMRN, what is OpenMRNLite, some comparisons, and then we go into a little bit of details of how you build devices with OpenMRNLite, and then later on I'm going to go into a couple of specific features. So OpenMRN is short for Open Model Railroad Network. This is a project that was started by Stuart Baker, and I'm one of the contributors there. It's an open source software package. Basically, it is available on GitHub. I put up the link, but if you search for OpenMRN, you're going to get it straight away with your favorite search engine. It has been very important from the very beginning on that this has to be a commercially friendly implementation of the OpenLCP or later LCC protocol suite. So this is using a BSD 2-clause license, which was specifically chosen so that it allows real manufacturers of model railroad electronics to build real products on top of that. This is started as OpenLCP, but eventually can venture into other protocols, although until now the primary focus has been on OpenLCP. But there is also a little bit of others, like we can create DCC packets, for example, as is very common to do with the command station. It is cross-platform library, so this is portable to a variety of different devices. It can run on 32 or 64-bit processors. It is written in C++, so it requires C++ 11 or newer standard. It is portable to a large variety of microcontrollers. We've run it on ARM, RISC-V, Tensilica, MIPS, you name it, we've probably run on it. And it can also run on a variety of desktop machines and operating systems. We're obviously running it under Linux, but it runs on Mac. It would run on a Raspberry Pi, on BeagleBone. We've run it actually. One of the most interesting ports that I've done was a WebAssembly port, which allows OpenMRN to actually run in a browser. So you can actually run a website on a browser, served by a web server, of course. And then this browser becomes a full-fledged node running OpenMRN inside the JavaScript virtual machine and being able to natively send and receive OpenLCP and LCC messages. So that was really cool. So that's the base library inside OpenMRN. And then we have a wide variety of support libraries for building actual MCU-based products. The most important one of these is a POSIX-compatible driver model with a full set of driver layers for a number of MCUs, including file systems, etc. And we have a matching cross-platform compilation and test infrastructure, which is based on Makefiles and has the ability to deal with, as I said, the variety of platforms that we have here. Let me go a little bit into some statistics. We started 13 years ago. We have 5,600 Git commits right now. If I look at just the current snapshot, it's about 70,000 lines of code and 40,000 lines of tests above that. We put a very, very big emphasis that every single feature that is part of the core protocol suite has to be tested. Because it is only these sets of tests that enable us to have responsible ongoing development while ensuring the quality of the software deployment. There are a variety of products are on the market that you can actually purchase right now that are built based on OpenMRN. So there are the TCS UWT throttles, the Wi-Fi throttles, the command station, the LCC command station from TCS, the CS105. The matching booster, the B106 DCC booster, the fast clock from LogicRail, the LCC version of their fast clock is built based on OpenMRN, and the most recent product is the Lite EFX, Lite Effects Pro from LogicRail, which is also built on OpenMRN. There are also a number of products that are announced but have not yet hit the market yet. the MRC command station, the entire next platform for MRC actually. So the command station, the handheld throttle, and the Wi-Fi gateway, these are all going to be Wi-Fi based products that speak LCC, and they're going to be they are being built on top of OpenMRN. TCS is also working on additional products, with active participation from us, on a wireless locomotive decoder, one that you can actually like build into a locomotive, and also a Wi-Fi gateway. Then there are some new folks coming on board, the LCC signals. If any of you have been to an NMRA convention in the last 2 years, you may have seen from Rick Lal the very interesting prototypes of his USNS CTC panels, and the backing electronics and the software behind that is also going to be built on OpenMRN. So this is OpenMRN. What is Lite? The Lite version is basically a simpler to use version for hobbyists, but it's built of the same code base. That's super important. That means that all of like the test coverage that we have built for the ongoing development of OpenMRNLite benefits from that. It actually is literally building from the same code. This is also open source, but I mean, really, it's just a copy of the source code. It is an Arduino or a platform IO library. It is up on the library manager. So if you go in Arduino and you type in OpenMRNLite, you will actually get the library. All you need to do is hash include OpenMRNLite.h, just like you would do with any other type of library. As I mentioned, this is a one-to-one export of the code base. So whenever we make a change in OpenMRNLite, we actually make it in OpenMRN. Then we just basically export the code again. I have also added a couple of example sketches to OpenMRNLite, but realistically, a lot of the examples from OpenMRN proper would actually be pretty reasonable to look at when looking at OpenMRNLite. Obviously, only the hardware interface layer is the big difference. So if we try to compare OpenMRN and OpenMRNLite, the most important differences are actually the surrounding ecosystem, not the LCC part. The LCC part is really the same. But in the surrounding ecosystem, if you look at OpenMRN, this is a heavyweight environment for professional embedded developers. So it has like a makefile-based compilation layer. We are exclusively using it on Linux, but you can also deal with it in a virtual machine as well. But this is generally a pretty high bar for hobbyists and enthusiasts. So OpenMRNLite is built on the Arduino build system. So you use the Arduino IDE or the command line build or the platform IO build system, and that works on any platform and is relatively easy to use. So it is much better accessible. Applications that are built on OpenMRN, they always work on bare metal. So we start with interrupt vector tables. We start with booting the processor. We start with setting up the clock. There is absolutely no operating system around that. For you using the Arduino environment, the Arduino core takes care of actually booting the microcontroller. And whichever microcontroller you're using, the respective Arduino core takes care of that. Also, when we are looking at sort of like basic drivers, talking to a serial port, etc., all of that we are usually doing with the vendor middleware from whatever microcontroller is being used. So for, let's say, Texas Instruments microcontroller, we use the TI middleware, TivoWare, or the SDK for like the MSPM zeros. From STM32, there are also the STM32Cube middleware layer, etc. Every vendor basically provides their own middlewares. For Arduino, this is also not a problem. Usually, if there is a middleware needed, you're not really aware of that, because if there is a middleware needed, it usually comes with the Arduino core. So you don't have to worry about how to access, like GPIO ports. You don't have to worry about what kind of register sets are there, what kind of header files you need to include for the MCU. All of that is taken care of for you. Our heavyweight OpenMRN applications, they are either running on POSIX operating systems like Linux, or if they are on MCUs, then they run on FreeRTOS. We also have like a little bit of like an abstraction layer between the particular operating system. So on FreeRTOS, we are actually emulating POSIX in a lot of different aspects. OpenMRNLite, it does not doesn't force you into any particular operating system. So it works with a completely normal Arduino mechanism in a single-threaded way, with just calling setup and loop commands in the OpenMRN code base. Also, there is a big difference with the drivers. For the supported microcontrollers in heavyweight OpenMRN, we have basically built a POSIX API emulation library for serial, I2C, SPI, etc. Also CAN bus for the MCUs that we are actually using with real manufacturers. On the other hand, if you look at the Arduino ecosystem, all of those libraries are basically given to you by the Arduino core. So the Arduino core comes with a serial library, with a serial USB library, with a wire library, with a SPI library. You don't have to worry about that. But that also means that you are basically bound to whatever library implementation the Arduino core brings to you. CAN drivers are actually very interesting. CAN drivers for real OpenMRN, we basically wrote our own CAN drivers, often using the middleware, but generally doing specific customization on top of that for seamless queuing, etc. Whereas in Arduino, there isn't really a standard CAN library. There are a large number of different CAN libraries in Arduino. So for your particular MCU, you'd have to be responsible for finding the CAN library in Arduino. For like 3 or 4 microcontrollers, I have actually gone and found appropriate CAN libraries for the Arduino and made use of that. And those are basically the fully supported hardware for OpenMRNLite. And then finally, the last interesting point is the storage. For OpenMRN production devices, we are typically using Flash for storage, and inside Flash we have to use wear leveling, EEPROM emulation, or some sort of like Flash file system. And we actually did that, so we implemented that in OpenMRN, but that's part of the driver layer. In Arduino, storage is really tricky. I think you have probably observed this by yourself as well. I'm going to come back to that a little bit later.